model. In the course of this video series, we have seen several ways to gain insight into chemical reactions with the help of atomistic modeling. In this video, we want to combine knowledge about elementary reaction steps into a microkinetic model. This will allow us to gain insights into the overall reaction system behavior. As usual, you can find a link to a detailed step-by-step tutorial in the YouTube video description. I will also add a link to an excellent introduction to microkinetic modeling written by Professor Filot. The reactive system we want to investigate is the oxidation of carbon monoxide to carbon dioxide on a catalyst surface. 4 individual reaction steps can be identified: the adsorption of carbon monoxide, oxygen and carbon dioxide, and the surface reaction from adsorbed oxygen and carbon monoxide to form carbon dioxide. These elementary reactions not only have their individual energy barriers and rate constants, they are also all coupled to each other. To obtain the temperature dependence of the overall reaction system, we can set up a microkinetic calculation with the MKMCXX program via the AMSKinetics interface. We begin by specifying the compounds in the left panel, where a distinction is made between gases and adsorbed compounds. An empty free surface site is referred to as a star, while an adsorbed species is marked with a star accordingly. We start with a 50-50 mix of carbon monoxide and oxygen and no carbon dioxide present. Now we can specify the elementary reactions. As a rule of thumb, we choose Arrhenius type equations for reactions that occur in the same phase, be it gas phase or adsorbed on the surface, while adsorption-desorption reactions are usually better described by Hertz-Knudsen type equations. After we fill in the parameters of the individual reactions, we can proceed to specify which properties we want to calculate. In our case, that will be the temperature dependence. For this, we set the temperature range from 300 to 800 K with a step of 25 K between individual simulations. To also calculate the orders, we check the orders checkbox and specify the main reactants and products in the according details panel. The calculation will only take a few seconds to finish. For our purpose of investigating the temperature dependence, we double-click on the file derivative.pdf inside the results folder to display the production or consumption of the reactants and products as a function of the temperature. Here we find that the optimal temperature for carbon dioxide production lies around 500 Kelvin. That's it for today. I hope you found this useful, and as always, we're happy to answer any questions or comments below this video.